Swayam Prabha. Digital India. Educated India.
Is that okay? Okay. So the third property is very important. So we are already giving one condition. The system X is equal to B is solvable if and only if B is in the column space of A. Is it? B is in the column space of A. Is solvable. That is, we are saying that this is consistent, right? System is consistent if B is in the column space of A. How to prove that? Is there is if and only if condition. It's not only that one direction, but if there is a solution, then this condition will be true. That is, B will be in the column space of A. And if this is in the column space of A, that will be then it will have a solution. So how to prove this? So let's just sketch the proof little bit. Go to the next slide. This is in the column space of A. So we are saying that this system, we are considering Ax is equal to B. Okay? Considering Ax is equal to B. Suppose this system has a solution. So then what? If this system has a solution, then we'll find some X. Say my X is say C, which is equal to C1, C2, Cn. So say this is the solution. So if there is a solution, then we will find such X, and for this we can write A of C equal to B. Right? So then you can write AC is what? This is equal to, this implies B equal to A1 vector. I write the column vectors what we have denoted there, plus C1, A2 vector, C2, AN vector, Cn. This implies what? B belongs to the column space of A. Similarly, if you just go the other way around, if B belongs to the column space of A, you can show that there exists a solution because we'll find a linear combination. So that's why this is the condition, right? If this right hand vector B belongs to the column space and by these column vectors of the matrix A, then your matrix, each system of equations is solvable. Now we want to find two more subspaces which will give us the complete understanding. Till now we have found that when the system of equations is solvable, but we haven't talked about that whether the system has infinitely many solutions or finite solutions. Okay. For that we need to understand more which are the null space of the matrix A. So what is null space of the matrix A? Yes. So if you consider the corresponding homogeneous system Ax equal to 0, so that is this, then find all the solutions of the corresponding homogeneous system. Homogeneous system is what? So the null space so this is called the non-homogeneous system when B is not 0. Right? The corresponding homogeneous system is okay. So you find all possible solutions of the homogeneous system. So that will give you a set of vectors in dimension in which vector space? R. X is in, so I am considering this vector space NA X such that Ax equal to 0. X, do you remember that it was in N, right? So this was in Rn. This was in Rn. Okay? Because we have how many columns? N columns. So we are multiplying this x1, x2, x2 till xn. So that will mean x will be in Rn. So this Na is a subspace of, this will be a subspace of Rn. How to prove this? This is just, I'm just stating it from the intuition. So how to prove this? So this Na is a subspace of Rn. You take two elements from Na and show that their linear combination is again in Na. You just take two elements, say V and W, from Na. You take two elements V and W from Na. So how they will look like, what property they will satisfy. So A V equal to 0, right? Since this is coming from Na, and A W equal to 0. So this is coming from, so this should satisfy this condition. No? Okay. So now what we have to show? We have to show that if we consider two scalars C and D, we have to show that CV1, CV plus DW belongs to Na. To show this. How to show this? You just apply the matrix operation on this element. So I just apply A CV plus DW. This is equal to, you know, how this matrix multiplication will be distributive, right? So you can just write CAV plus DAW. This is 0. The right hand side, this is 0. This is 0 because these two conditions are satisfied. This is 0, right? Is it okay? Is that okay? Okay. So this implies CV plus DW belongs to. No? So we have got another subspace. We have got another subspace of Rn. So for Rn now we have two subspaces. One is CA transpose, another one is Na. Two subspaces. Similarly, we'll have two subspaces on Rn. One is the CA, and another one will be denoting. I haven't yet denoted here, but if you consider, so one is another one corresponding to the rows, space. We'll have another one. So this is called the left null space, A transpose. So that is called the left null space. Left. So this is a subspace of R. Similarly, we have, as we have proved, this Na is a subspace of Rn. You can also prove that Na transpose is a subspace of Rn. Okay. So one thing you can notice that Na contains the 0 vector, right? Because A is 0 equal to 0. If you multiply with 0 vector, so 0 will be always the solution of the homogeneous system. So that's why this will be a subspace. But if you consider AB the non-homogeneous system for B not equal to 0, so that will not be a subspace because that will not contain the. So this for the non-homogeneous system when B not equal to 0, so 0 vector will not be a solution of that system, right? So that's why your the solution space of the corresponding to the non-homogeneous system will never be a subspace. Will never be a subspace because that will not contain the 0. So this is a very important property we need to understand. Okay, we have seen the null space, but given a matrix, how to compute the null space? Given a matrix, so matrix A, how to compute the null space? Um, but instead of understanding this terminology, let us see one example so that will be better. Right? So let us see one example. So suppose we are given this this matrix A, and then what is my null space? How we can compute? So I need to write it 1, 2, 2, 4. Let's write it 1, 2, 2, 4, 3, 8. Let's try to find the null space of this is really tricky. So A, tell me 1, 2, 2, 4, 3, 8, 6, 16. Okay, so we are given this, we want to find the null space of this matrix. So I think you have learned, whoever has done the linear algebra, some kind of reduction of how we can do some matrix operation, right? To reduce the matrix to a little bit simpler form. Right? So what we do with this? We do this row operations, right? What is the first row? Or what is the first non-zero element? First non-zero element in a row is called the pivot. So here what is the pivot for the first row? 1. So this is my pivot. So 1 term is the pivot. And then what we do? We just eliminate by multiplying we eliminate we make the other entries of that pivot column. So this is my pivot column, right? So this is my pivot column. We make the other entry 0 by multiplying. This is the multiplier. C is the multiplier. So what we do, we just take the second, the first row we keep as it is. For the second row, we subtract the multiplication of the first. You multiply by 3 the first row and then subtract. Right. So this will be 0, 6, 2, 0, and then 4. So what we do, we do R2 minus 3 into R1. So this is the operation we do. So there are a lot of different properties, but we can show that if you are given a matrix, the main important properties are not changed if you do this kind of operations. So that you can prove mathematically, but I will just keep this for you to check. So now what is the pivot for the second row? 2, right? So these 2 are my pivot columns. We call this pivot columns. Pivot columns. But these 2, there is another one, right? Do I need to introduce that term? So I call this the free columns. Free columns. Okay. So for the null space, what we need to do? We need to find the solutions of Ax equal to 0, right? So that is our goal. So Ax will be from dimension R4, right? So it is from R4. So we write it x1, x2, x3, x4. Now, these components of x corresponding to the pivot columns are called pivot variables. So, these two are my pivot variables. Pivot variables. Whereas these two are called free variables. Free variables. So the idea is you choose the free variables in some special way, and so you fix the free variables, and then you solve the rest of the equations to find the pivot variables. So what are the special ways of selecting free variables? You choose first x3 and x4 are the free variables. First choose x3 is equal to 1, x4 is equal to 0, and next x3 is equal to 0, x4 is equal to 1. Okay, so we choose free variables, we choose first special. So we call this the special solutions. So corresponding to each choice of the free variables, we will be getting a solution that will be called a special solution. Solutions. So first you choose x3 is equal to 1, x4 equal to 0. Okay, and then you find what is your solution for this equation. So x1 plus 2 x2 plus 2 equal to 0, and then x2 equal to 0. Right? So this will give you, so from here what you will be getting, x1 equal to minus 2. So now you get one solution from here. Using this choice you are getting one solution. We write it S1 is x1 is minus 2, x2 is 0, x3 is 1, x4 is 0. So that is your one solution. It's called a special solution. Another special solution, if you choose x3 equal to 0, x4 equal to 1. Okay, what you'll get? You'll get can you check it? What will be your S2? What will be your S2 then? 0, minus 2, 0, 1. Are you getting this? I haven't done the computation. You are getting this, right? So you can see that if you have, say, three free variables, then how you have to choose? 1, 0, 0, 0, 1, 0, 0, 0, 1. Okay. So you'll get three solutions, three special solutions. And you can see that there is a term we will be introducing. So these three solutions are independent. They are not one, you cannot express as a linear combination of the other two solutions. Okay. So what is now your null space? So after you compute the special solutions, your null space will be the span of those special solutions. So your null space will be, right, is the span of the special solutions, linear span of the special solutions. So that is here what we are getting, this is equal to, you just take two scalar quantity C and D, say, or usually a kind of tradition is like that, we choose the these variables as same as the free variable symbols, like x3 and x4. So it will be x3 into s1 vector plus x4 into s2 vector, where x3 and x4 belongs to somebody. So this is your the null space. Okay. So this is how we will be computing the null space. But this understanding of how we are computing will be give you the information what will be the dimension of this space. So that we will be discussing later. But you just notice that here S1 and S2, the way we have selected the free variables, they are not dependent to each other. I mean, you need to find all those free variables to get the complete null space. Is that clear? So yes. If you are having 2 by 5 matrix, so number of rows is 2 and number of columns are 5, then how many free variables will be there? You can have, depending on the matrix, if you are at most how many you can ask that at most how many free variables I can have. 3. Right? I mean, if these two, there will be one new definition will be coming as linearly independent, linearly dependent. If your row vectors are linearly independent, then you can have how many pivots at most? 2 pivots. And rest of the columns will be the 3 columns. Corresponding to 3 columns, you have 3 variables. But you can also have only, or you can also have 4 3 variables if your row vectors are dependent. That is, one row vector is a multiplication of the scalar multiplication of the other row vector. In that case, you will have only one pivot. So, number of free variables will be total number of variables minus number of pivot variables. At most there will be 2, but there could be also 1. Right? Okay. So, as I have expressed here, your the null space is all linear combinations of those spatial solutions, and that is your the null space. Okay, so what we need to understand. So basically, our goal was to understand those 4 fundamental subspaces corresponding to a given matrix and their dimensions, right? To understand the dimensions completely, we also need to understand the true size of the given matrix. That is the rank of the matrix. How many of you are already familiar with rank? You are familiar with rank. I'll not go into the details as I already have given this topic as a prerequisite. So I'll assume that you know how to compute the rank of the matrix. So the way I have computed the null space is by yes. Okay. 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 But I think most of you already are familiar how to compute rank. Raise your hand who don't know how to compute rank. So I'll go quickly, but I will not be computing it using the example. So what do we compute? We compute the true size. So we know that how we can compute the pivots, right? So the rank is the number of pivots in a matrix. Okay, like in the what was the rank of the previous matrix? What we have just computed the null space? 2, right? Because we got 2 pivots. We do all the elimination, and then we see that how many pivots are there in the matrix. So that will be your rank of the matrix. Okay, so that is also called the true size. Basically, we are eliminating all those equations which are kind of redundant, which has no function in your equation system of equations. Okay, so this the elementary row operations you have already seen. Although I have so after the just give you two metrics. Basically, when we apply the elementary row operations on a matrix, we'll be getting different kinds of metrics in different stages. So there are two names which are important. One is the row reduced matrix. Row reduced matrix is if you just do the elementary operations 2 and 3. So that is the scalar multiplication of a row and addition of a row with the scalar multiplication of some other row. But you do not interchange the rows. Okay? So if you apply only 2 and 3 from this set of the 3 elementary row operations, then you will be getting so this is an example. You can see the example of this matrix. So this is called the row reduced, where you have reduced, but you haven't interchanged to make it kind of very systematic. That one will be the this here. If you interchange it, you will get a little bit better matrix to see immediately that this matrix will be your identity matrix. Okay, so this is called the row reduced matrix. So the first non-zero element in a non-zero row is 1, and each column containing the leading one, the other elements will be the 0. So the first non-zero element will be 1, and the other elements are 0. Here the first element is 1, the other element is 0. And here first element will be 1, and the other element will be 0. So this is called the row reduced. Now, if you also, in addition to this, if you also do the interchange operation, so you'll be getting a better matrix. So that will be called row reduced echelon matrix. So that is the matrix we'll be aiming for when we'll be doing the this elementary row operations. And you see that this is the row reduced echelon matrix from this matrix after doing all the elementary row operations. And you see that in this, you can see that this is the identity matrix, right? This is the identity matrix, and this number of leading ones in each row are actually having this order. So that's why what we are getting from the size of this matrix, we can say what is the rank of it. Right? From this size of this identity matrix will be the rank of the matrix. So there are few properties. I'll be just quickly showing them. So one property is the rank of a matrix remains invariant. So that I already have told under the elementary row operations. When you apply any elementary row operation, the rank of the original matrix that doesn't change. Okay. The second property is that so that is why you can say that rank of the row reduced echelon matrix say R. So that is the number of pivots in that row reduced echelon matrix. So that will be your rank of the original matrix A. So rank of A is same as the rank of R is equal to that number of pivots in the row reduced echelon matrix. So that is your rank of the. So this is how we will be computing the rank of a matrix. So we will do reduce the original matrix to a row reduced echelon matrix and see that how many leading ones are there or how many pivots are there. So that will be your. So you can just try this matrix to find the rank of this matrix, and at the same time you can also see how to compute the inverse of this matrix. 5 minutes. Okay. I started 15 minutes late. Can I take? Okay. Okay. So I think we'll just try to finish it. And then rest of the things I will move to the next lecture. Anyone can get see that how we can find the inverse of this matrix using the elementary row operations. How? So this is your matrix. I'll just sketch it. So this is a 3 by 3 matrix. We want to find the. So what you will do? You will just consider another I3, and then you do all the elementary row operations, and the left hand side will be your I3, and the right hand side will be. So you know this. Okay, so I think after introducing the rank, I think one more thing we need to understand, that is the independence. So that is what I was talking all the time. And so this will be finally giving you the dimensions of your subspaces, what you have considered. And you also need the rank. So basically we'll be relating the rank and these dimensions of these subspaces. So when we say that the set of vectors v1, v2, vn are linearly independent, because if you have only the zero scalars, 0 into v1, 0 into v2, 0 into vn, which will be giving you the 0. The only possible scalars which will be giving you the 0 vector is the zeros. Okay. In other words, you can express this system will have the solution. Only solution will be C1 equal to C2 equal to C. We want to understand the linearly independence of the column vectors of the matrix, because we want to understand the dimension. So the column vectors of the matrix A are linearly independent when this system will have Ax is equal to 0. So this is your homogeneous system, right? So it is same as that whatever I have written in that this row. So this is equal to 0 only for x equal to 0. In other words, what you can say, the null space of the matrix A is the 0 vector. So only element in the null space is the 0 vector. So then we say that the set of column vectors are linearly independent. You can check that this set of vectors are linearly independent. How can you check? You just take any scalar multiplier. So you just check 1 0 0, right? The standard one, C1 plus C2 into 0 1 0 plus C3 into 0 0 1 to 0 0 0. So what's the, if you solve this system, what will be that? C1 equal to 0, C2 equal to 0. This is the only possible solution, right? So this will take that these three vectors, this set is linearly independent if the rank of this, if we consider these are the column vectors, right? So this is the rank will be 3. Is it easy to check? Yeah? I'll leave it for you to check. Okay, so there are two more terminologies: the full column rank and full row rank. When we say that the matrix has the full column rank, when your the number of independent column vectors will be the rank of the matrix, right? Similarly, for the full row rank, the number of independent row vectors will be the full, right? So we'll see that how this will be affecting your number of solutions in the system of linear equations. Is it the time? So I should stop now for the tea break, and then I'll continue from here because we need to understand the dimension. It will take a little bit more time. Okay, I'll start from this slide number 22 from the next class.